All right, we got chapter 2 review here. All right, first question, and again, I've got limited time, so we'll go through this. It's a good review. Now again, as we go through this, I'll go through what's on your chapter test. I mean, there's a mix of a little chapter 1, mostly chapter 2, and a little bit of a look at the chapter 3. But I picked some key concepts out of each chapter just so you remember and retain this material. And some of this material in chapter 1 kind of builds in chapter 2, and we're going to look at the bigger picture, look at the relationship, okay? So we're going to take a step back for a minute. And again, this is mostly chapter 1, this first question, but listen to what I talk about as we go through it, okay? So the first question said, describe the overall basics of the periodic table, include the following: metals, nonmetals, metalloids, reactivity, trans groups, periods, okay? We already know groups are vertical columns. They all have the same number of valence electrons. They react the same way. We are family. Hey, 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 I got all my valence with me. Whoa, whoa, whoa. Again, all elements in a group or family have the same number of valence electrons. Vertical columns. They're the alkaline metals, the alkaline earth metals, and so on and so forth. And then as you go across, you've got periods. They go across. They're arranged by increasing number of valence electrons and atomic number. Okay. Reactivity overall, you have the zigzag. Left side of the periodic table are metals. Right side are nonmetals. Right on the zigzag, you've got the metalloids, which show properties of both metals and nonmetals. Now, the most reactive metals are on the left, the alkaline metals. Alkaline earth metals are the second most reactive. It goes 1 valence electron to 2, and then groups 3 through 12. You've got transition metals. So overall, the reactivity of metals decreases as you go from left to right up to the zigzag. Alkaline metals being the most reactive, 1 valence electron, boom, right away they get rid of them. Group 2, 2 valence electrons. Not only do they need to get rid of 1, they've got to get rid of 2. And then you've got transition metals, which tend to rust in the wind. All we are is rust in the wind. Oh, oh. Now, let's think for a minute. Gee, metals on the left tend to react with what? To form, chapter 2, an ionic compound. And we learned that these metals, the alkaline metals, the alkaline earth metals, right, group 13 aluminum, also form ions by giving away valence electrons to nonmetals. And they form an ionic bond. Oh, ionic compounds, metals, nonmetals, through the transfer of valence electrons, okay? So let me go through the properties of these metals real quick, and we'll come back to that. So metals, shiny, hard, lustrous, okay? Malleable, can be pounded into different shapes with a mallet, okay? Ductile, can be drawn out to a wire. Good conductor of electricity. Oh, remember we learned this in chapter 2? Metallic bonding. And we talked about atoms of metals all combined together. And there's a flow of electrons back and forth between all the different atoms of those metals. Okay, that flow of electrons is electricity. Okay, and that's why they're good conductors of electricity. They also have a very high melting point and are solids at room temperature. Why? Because of their metallic bonds. They don't want to give up what they have going together. They are sharing electrons back and forth. It's a great situation. It's going to take a lot of heat to separate them apart. Okay, so that's where metallic bonding comes into play. Also, they can be easily shaped. Okay, know that with malleable in solid room temperature. Nonmetals are the opposite, dull, brittle, insulators, and also solids, liquids, and gases at room temperature. Okay? So we talked about those properties. Metalloids show properties of both metals and nonmetals. Semiconductors are good examples. Okay, so we talked about the reactivity of metals. From left to right, they give away valence electrons. They tend to form cations, positively charged ions. Why? Because they give away their electrons. They've got less electrons and protons, so they're positively charged. Now nonmetals to the right of the zigzag, they increase in their reactivity all the way up to the halogens, the wackadoos, the nutcases. They have 7 valence electrons, okay? They're 1 away from being stable. Where do they get them from usually? Usually in an ionic compound, they'll get them from a metal. Sometimes they can react by themselves. We'll get to that a little bit later. But they all aspire to be like the snobs, the noble gases, who have a full outer shell. Except for, well, they all do, except for one little exception right here. Helium. They have a full outer shell, but they've got 2. The rest have 8. Okay? So again, we had the song, all I want for science is a full outer shell, a full outer shell, yeah, a full outer shell. Gee, if I could only have a full outer shell, then I would be a stable substance. Now in chapter 2, you've learned, well, how do they become a full outer shell? By transferring valence electrons or by sharing in a covalent bond, okay? So the first chapter, that's why I put this up here. Here are the properties of the periodic table, the number of valence electrons, metals, nonmetals, great, wonderful. Now chapter 2 gets into how they become stable, and we're going to talk about that right now. Okay, so I pretty much hit the first question, and we set it up for question number 2. Now, I gotta move my camera. My tripod today is the overhead, and it works rather well, so here we go. I'm going to move the overhead card. Watch this. Here we go. Watch it. Whoop. Oh, look at that. Uh-oh. Let me zoom out a bit. Okay, now this gets into chapter 2. Wow, look at that. Whoops. Whoa. Okay. So now chapter 2. See, chapter 1 gives you the basics, metal, non-metal. Yes, I'm writing over here, you probably can't see it. Chapter 2 talks about once valence electrons move, whether they're transferred or whether they're shared. Okay, so let's talk about the transfer. Ionic compounds usually form with a metal and non-metal. Oh, geez. The alkaline metals, or the alkaline earth metals, love to react with the halogens or elements in the oxygen or nitrogen family. Okay? So they're very reactive. It's a transfer of valence electrons. The metals usually want to lose valence electrons. Well, where do they go? They go to the nonmetals where those are gained. Okay? They also have a strong intermolecular force in a crystalline structure and dissolve in water. Let's talk about this. We talked about before how NaCl, right? Here's your alkaline metal. Here's your halogen. Sodium gives one valence electron to chlorine. So sodium becomes the positively charged cation. Chlorine becomes a negatively charged anion. We call that sodium chloride. Okay? But you've got to understand, this bond is pretty strong. It's strong. But when you have table salt, you just don't eat like one compound. You eat a lot of them. Well, how do they arrange themselves? Since they're polar, there's polarity here, beyond polarity. Beyond that, they tend to arrange themselves as such in a specific pattern, like this. And you notice there's an attraction right here. There's an attraction right here. There's an attraction right here. This yellow squiggle, if you can see that, is the intermolecular force. Okay? These forces right here, given the fact that this positive end wants to be near this negative end, two different compounds, it's going to take a lot of heat to separate that apart. So that's why they've got strong intermolecular forces right here. Okay? They form a distinct pattern, crystalline structure. It's going to take a lot of heat. So hold on, they have a high melting point. Why? Because it's going to take a lot of heat to bring those apart. Okay? But also, too, they can easily dissolve in water. If you were to take one of these blocks and drop it in water, they separate. And the reason why we showed this in class. Remember when I said, here, take this valence electron, pound fists. Well, it's a pretty strong bond, but when you put them in water, they'll break apart. Okay? And they'll be surrounded by the water molecule. So I'm going to erase this part over here if I have any room. Hold on, let me zoom out. Give me a second. It's not easy to do. Hold on. There. Okay. We talked about, here's the beaker. Here comes sodium ion in water. Here's chlorine over here in blue. How's water going to dissolve it? Water's going to put its negative end, which is oxygen. We talked about this. And surround it so the negative end, the polar negative end, likes this charged ion. So the oxygen goes near the positive sodium. While near the chlorine, water surrounds it also. But you're not going to put the negatively charged end next to chlorine because you've got excess electrons here and excess electrons here. Too many electrons, they tend to repel. Repel, R-E-P-E-L, remember that word? They repel each other. So instead, the water molecule turns around and goes like this. Like that, showing its positive ends toward the hydrogen. So there's an attraction between the chlorine ion and the hydrogen ends of the water molecule, okay? And that's how they dissolve in water, okay? So the positive ends surround the negative ion, the anion. The negative ends of water surround the positive ion. So again, polar water loves charged substances. Almost like polar loving polar. Okay, when the ion comes in here, it's hydrophilic. It loves water. Dissolves, loves to be surrounded by it. Okay, polar, polar. All right, and again, we talked about ionic compounds beyond polar. Okay, they dissolve very well. And because of that, these flow everywhere. These ions, these charged particles flow all over this beaker. And the flow of charged particles is electricity. So they not only dissolve in water, they conduct heat and electricity when they have dissolved particles. Because they love to flow around. Charged particles flowing all throughout conduction of electricity. Okay? And then we talked about molecular compounds. It's only, hold on, let me move my tripod, overhead. Who knows what I have here? Here at Springford, here we go. Woohoo! Look at that. Now we've got molecular compounds, 2 or more nonmetals. Okay? Nonmetals from the right side, because they form a strong covalent bond, and I'll come back to that. Okay? And are there intermolecular forces? Sure there are, if they're polar usually, but they're weaker, and we'll get into that with water. Are they flammable? Absolutely, because a lot of CH compounds, hydrocarbons, they're nonpolar, and we've talked about that in class in terms of why they're nonpolar. Their electronegativity difference isn't much, and there's no excess valence electrons. You react them with oxygen, they burn very easily. Most do not dissolve in water, and most do not conduct electricity because they're nonpolar. There's no excess electronegativity. Okay, so I'm going to erase this, and I'm going to move on to the next question and bring more of this together. Hold on. So then, why do ionic compounds transfer valence electrons, molecular compounds share? Look here. Here's ionic. Here's molecular, or covalent. Here we go. Ionic is a transfer of valence electrons. So if I've got magnesium, and I've got a positive 2 charge, and I've got oxygen with a negative 2 charge, the compound is magnesium oxide. We know that. So magnesium has 2 valence electrons, oxygen has 6. What does magnesium want to do to become stable? It wants to lose 2. Oxygen wants to gain 2. Let me make sure that shows up on the camera, since this is a one-man show here, and we have minimal equipment. Okay, let me move that in a little bit here. All right, good job. Woo-hoo. So, looking at this, magnesium wants to lose 2. So it'll say, here you go, oxygen, take that. Here you go, oxygen, take that. This magnesium is now happy. This oxygen is now happy. Because of a transfer of valence electrons. They have opposite needs. So now magnesium has a positive 2 charge, oxygen has a negative 2 charge. Because this lost 2 valence electrons, this gained 2. So it's a metal, non-metal. Again, metals have usually 1, 2, or 3 valence electrons. It's easy for them to lose them, not gain them. Whereas the non-metals, they're usually at 5, 6, 7. They want to gain. That's the quickest way. So ionic compounds, opposites attract, okay? Whereas in a molecular compound, they share because usually they have similar needs. So let's say I've got a diatomic molecule. Let's say I've got F2, fluorine gas. Fluorine has 7, right? Another fluorine has 7. So fluorine says I need 1. This fluorine says I need 1. Whereas before, I want to lose 2, gain 2. Here you go, bro. Boom, boom, done. Pound fists. Here, this fluorine's like, yo, bro, give me your valence electron now. Fluorine's like, back off, punk. Give me yours. No! So they fight. But eventually they, because they have similar needs, they cooperate and form a covalent bond, and they share. So this fluorine forms one covalent bond, right? Shares. They have one shared pair of electrons. Now this bond is strong. It's strong because fluorine isn't going to let go. Because keep in mind over here, magnesium gave 2 oxygen. Oxygen now has 2 valence electrons. Magnesium's like, take it, pound fist. Good job, bro. They go in the water, they dissociate, they break apart. Here, dude, this fluorine ain't letting go, nor is this one. They fought for that. They finally came to an agreement. Strong bond. Okay? Very strong bond. So they have similar needs in a molecular compound, therefore they engage in usually a covalent bond. Okay? And then here, next question. Oh, when 2 individual substances form a covalent or ionic compound, is it a physical or chemical change? It's chemical change. 2 individual substances rearrange their chemical bonds to form new ones. That's a chemical change. Okay? When an ionic compound dissolves in water, do they revert to their original state or do they stay as ions? Okay, we're running out of time here. When they drop in the water, the ions, as we showed over there, they break apart, but they stay as ions. They stay in their current state. Water's just in their way, interacting with them. So it's a physical change because once the water goes bye-bye, they revert back to their original form. So when an ionic compound dissolves in water, right, they stay as ions, because dude, why would they want the electron back? They gave it away, and this one, the other one took it. You think they're going to want to go back to being unstable? I don't think so. But when water comes around, right, with the ends that are polar, you know, the negative and positive ends, they're going to hang out and be surrounded. But when the water goes bye-bye, they're back together again. So that's a physical change. Okay. What's the total number of electrons? Here's a review. In the following, Sr2+, and nitrogen, nitride. So strontium, you look on the periodic table, its atomic number is 38. So you would think for an atom, its atomic number is 38, it's got 38 electrons, but its ion, 2+, 36 electrons, okay? For nitrogen, its atom, its atomic number is 10, right? So it's got 10 electrons. Oh my gosh, did I just have a major break? Thank you. Atomic number 7, brain fart, excuse me. Atomic number 7. Yeah, I know, I can read. I'm looking ahead. Atomic number 7. So it's got 7 electrons. 7 protons, 7 electrons, because all atoms have a neutral charge. But when they form an ion of -3, 10 electrons. Because they've got 5 valence electrons, they want to gain 3 to become stable. 2 in the first shell, 5 in the second. Okay? For indium, electron configuration, I'll read it off to you. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p1. How do you do the shorthand? Go to krypton, put a bracket, brace, whatever you want to call it, around krypton, and start at 5s2, 4d10, 5p1. Okay? That's that. Next page. Here's 10 water molecules. Look here. I'm going to draw a couple. I don't have time to draw 10. Running out of time. We'll draw one more. Okay. Look here. Notice what I'm doing here. Ask yourself, what is the green squiggle line? What is the green squiggle line? The green squiggle line is the intermolecular force. It's the hydrogen bond in the intermolecular force method. Now look here. Here is water. Water is arranged, it's a polar substance because there's excess valence electrons, negative charge toward the oxygen, negative charge toward the oxygen. So when they arrange themselves, the negative ends of water tend to kind of have an attraction with the positive ends of water, where the hydrogen is. So they arrange themselves. I would draw more, but again, I'm running out of time. So this is the intermolecular force right here. Now, how do we separate these water molecules? You add heat, and when heat's added to water molecules, heat makes these molecules move faster. And when they move faster, they expand. And what will eventually happen is these forces are not as prevalent because they're moving away from each other. Okay? So when you add heat, the intermolecular force breaks down. Is that a physical or chemical change? When we're decreasing the IMF, when we're adding heat, this is a phase change. And it's a physical change. As we add heat, we're breaking apart the molecules. Okay? But what happens when the molecules slow down? Well, they start to go back together again. They compact or condense together. Well, how do they arrange themselves? Is this oxygen going to want to go near that oxygen? No, because the electrons repel each other. They're going to want to go where opposites attract. So when it cools down, the intermolecular force reestablishes itself, and they get closer together, and they arrange by opposites. Opposites attract. So those are hydrogen bonds. So, okay. So as you add heat, the intermolecular force is decreased because the molecules thermally expand because they add energy. When heat leaves the system, water starts to condense. Well, if they're going to be close to each other, they better arrange themselves a certain way. Opposites attract. Polar loves polar, but opposite ends within polar, that's how they arrange. Okay? Now, how would I make this a chemical change? Do I alter the squiggle line thingamajiggies? Or do I break the bond? When you break a bond of water, that's when you have a chemical change. So doing this gives you a chemical change. And we'll get into that next chapter. H2O decomposes to hydrogen gas and oxygen gas. But again, breaking that chemical bond is a chemical change, right? Decreasing or increasing the intermolecular force is just a phase change. They thermally expand when there's less IMF. When there's more IMF, they're closer together because opposite ends attract each other. Now again, this gives water's property of cohesion. Water molecules like to be near each other. They stick to each other, or they stick near each other because of their strong intermolecular forces that they have. Okay? All right. Let's go through a couple more of these. Copper 1 dichromate. And again, with the transition metal, I will give you the information for your test. So copper 1 dichromate, Cu+, dichromate, we've got Cr2O7, 2 negative. Okay, so I've got a positive 1 charge, I've got a negative 2 charge here. But I need another copper. So my answer is Cu2, Cr2O7. There's your final answer for that one. Potassium permanganate, give you a second. Potassium permanganate, K plus MnO4 negative. Uh-oh, EOA, EOA. Opposite, equal opposite. KMnO4. Silver sulfate. On your chart, Ag positive 1. Sulfate, SO4 2 negative. Again, how many silvers? Ag2SO4. There's your final answer right there. Ag2SO4. Sodium cyanide. Sodium cyanide is NaCN. Sodium cyanide is NaCN. Real quick, what if I said magnesium cyanide? What if I said that? Uh-oh, uh-oh, uh-oh. Be careful. This is why you should do the long trick. How many cyanides? 2. How many magnesiums? 1. It's MgCN2? No, parentheses. Be careful, be careful, be careful of that. Sodium hypochlorite, NaClO. Strontium carbonate, real quick. EOA, EOA. SrCO3. Okay, next section. Tin, 1 tin. Am I looking at the camera? Here it is. Hello, I'm here. Tin, I hope the camera didn't conk out on me because I'll be really mad if I'm doing all this for nothing. I really hope not, like it does all the time. Tin tetrabromide, TETRA, 4 for bromine. Iron 2, Roman numeral 2, carbonate. Again, reverse it. Look at your polyatomic ion, it's CO3. Iron 2 carbonate. Next one, aluminum chlorate. Again, aluminum chlorate. Well, what's chlorate? ClO3 negative. What's aluminum? Al3 plus. Well, you're given your formula there. Look here. AlClO3, aluminum chlorate. Potassium permanganate is the next one. I already gave you that one before. Gold, Roman numeral 3, chlorate, and ammonium bromide. Next 3, sodium nitride, Na3N. You draw 3 sodium atoms, giving 1 valence electron each to nitrogen, who needs 3. Aluminum sulfide, Al2S3. Again, 2 aluminum atoms with 3 valence electrons, giving each sulfur has 6, giving 2 to each sulfur. Calcium oxide, EOA, EOA, CaO. Next one, what's chlorine dioxide? Chlorine dioxide, what's 1 chlorine, Cl, nonmetal dioxide, O2. Antimony, Sb in the house, antimony, Sb, 1 antimony. Tri-bromide. Phosphorus, P. Triiodide? No, I don't want to triiodide. Ha! Phosphorus sulfur. What the heck is this thing? P4S5. Geez, guys, it's called prefixes. P4 tetra. Phosphorus. Pentasulfide. Again, I'll give you those prefixes. SEC, selenium. 6 fluorines. Oh, hexa. Selenium hexafluoride and diboron monosilicide. Diboron monosilicide. Next one. Draw them. H2S, hydrogen sulfide, real quick. Easy. Okay. Negative N, positive N, positive N. It's polar. What's the bond polarity? If I'm not mistaken, I don't have the chart in front of me. The bond polarity is a 0.5 difference. It's polar. And overall, the symmetry, look at this N, has excess valence. The compound is polar. Next one, PF3. Okay, polar this way. These are symmetrical. This has 2 excess, this has 6 excess. The bond polarity looks like it's a difference of 2.2, and it's polar. And O2 is a diatomic molecule. Bond polarity, non-polar, because it's a zero difference. Okay, chapter 3, foreshadow. That is already balanced, believe it or not. And it's decomposition.